And the reason is essentially that you have some ignorance in some parts, but that ignorance is correlated with some other ignorance you have in the other part. If you look only at the other part, but if you look at the whole, you have a complete picture which produces a more predictable and precise state. Now, this might have looked a little abstract, so since it was a bit abstract, let me just describe it with an analogy, because it's an important point for the rest of the lecture. And imagine that somebody tells you a portion of a sentence. So let's say Mary stepped out of her, and then you can decide how to complete the sentence. Any volunteer to complete the sentence? Want to complete the sentence? Bloomers. What? Good, so that's one possibility. Okay, so you can complete, and we'll all perhaps come with different ways of completing this sentence. And so we have a certain lack of information of what the sentence is. There are many possibilities for what lies outside the sentence. So we cannot say what the sentence means. It doesn't have a definite meaning, definite, clear, crisp meaning. Now, we know it involves Mary, but we don't know the full meaning. It could end in different ways. But if someone told you the full sentence, let's say Mary stepped out of her comfort zone by explaining quantum physics to a group of investors, then you have the full meaning. Now it's clear what the whole thing is. So if you have the whole picture, clear meaning. If you have only a small picture, so that's similar to looking at the portion of the vacuum versus the full vacuum. Okay, so in that case, you get a well-formed sentence. You have a portion, we lack some information. And in fact, there is a way to quantify the information we lack. So in the case of the sentence, we could imagine listing all the possible ways to complete it. Some will be very improbable, some will be more probable. And we can quantify, there is a well-defined way to quantify the entropy or the lack of information that we have. Using so-called information theory, we can assign a number to, roughly speaking, counting the number of different ways in which it can end. So I said the vacuum is then in this analogy like a well-formed sentence. So now let's return back to black holes. And so this is a picture of the space-time geometry around the black hole. Remember, roughly time is roughly like this, and space is roughly like horizontally. Exactly what you call space and time depend on how you are moving, but roughly speaking is that. So each point here is an event that happens in a space-time. Light rays are moving at 45 degrees. And this region here is the outside of the black hole. And if you are here, is the region that looks like flat space far away. So if you have a light ray that is coming out, it will go out like this. So here, this direction, you can think of it as the direction that comes out of the black hole. So, and then there is, if you are at some event here and you shoot a light ray going outwards, that light ray will go up, but then eventually it will collapse into a singularity. So we have here a singularity in the future. So this is a bit like a big crunch. So the interior of a black hole looks like a big crunch geometry where the universe collapses at some finite time. So if you're traveling here as an observer, you find that your universe collapses and you die when you get to the singularity. So I'm sorry, that's what general relativity says. Okay, so and not only do you die, but there is no way to escape from this according to general relativity. What was the question? Yeah, that's right. You can't escape because that would require you to travel faster than the speed of light. So the speed of light moves here at 45 degrees. If you wanted to escape, you would have indeed to travel faster than the speed of light. Absolutely correct. Okay, so that's the space-time geometry. And there is a particular light ray, which is the one that divides the region from which you can escape from the region where you, so the region where you can escape, which is this one outside, from the region where you cannot escape. And we call that the horizon. So this is some light ray. And so if you are an outside observer, you can see only a portion of the geometry, so the portion that is outside, because the points here, the events that are inside, can never send you a signal. So you ignore what happened here in the interior. You can only measure what happens here in the exterior. So we had the vacuum of space-time, the whole space-time vacuum, and it's split by the horizon into two pieces, the piece outside and some piece inside. And so we have a phenomenon similar to what we had with the sentence, in the sentence analogy, where we get only a portion. And because we get this portion, it leads to some ignorance, some randomness. And in physics, this ignorance or randomness translates into temperature. So whenever we have something at finite temperature, we have this feature. And the quantification of this lack of information is sometimes called entropy or disorder, is what the lack of information of what's inside. Now, from the black hole, we can calculate this entropy or amount of disorder using the laws of thermodynamics. So Hawking gave us the formula for the temperature of the black hole as a function of its mass or its energy. And then we use the laws of thermodynamics, and we can get an entropy. And it turns out that the entropy has a very simple formula, which is just the area of this horizon. So this is like a sphere. It's the trajectory of those light rays. And it's the area, so the area has some dimensions of length, and divided by that Planck length, the same quantity that Planck had originally thought that it might play an important role, here indeed plays an important role and appears in this formula. Of course, since this distance is very tiny, if you have a macroscopic area, this is a huge, huge, huge entropy. In fact, if you were to calculate the entropy of the universe, most of the entropy of the universe comes from the entropy of the big black holes at the center of galaxies. That is more important than any other entropy. And then the second law of thermodynamics would imply that the area should increase. And indeed, the laws of general relativity say that the area always increases. So Hawking had shown, even before this formula was developed, that if you have a horizon, the area of the horizon always increases. That this just comes from solving Einstein's equations, those equations that we discussed before, that have nothing to do with thermodynamics. So it's an interesting consistency picture. Okay, so black holes emit radiation, they lose mass. We call that evaporation. Now this, as I said, was irrelevant for an astrophysical black hole. But let's imagine someone let's say someone came and had some way of making a very small black hole, let's say a 1 kilogram black hole. And so someone gives you this 1 kilogram black hole, and you would say, well, 1 kilogram black hole cannot attract me very much. It's probably not a big problem. Okay? However, due to this effect, the 1 kilogram black hole, using the formula E equal to mc squared, will evaporate and will emit an energy which is equal to its mass. And that energy, if you work out what it is just like a 20 megaton nuclear bomb. So don't accept the 1 kilogram black hole from anyone. Fortunately, there are no such black holes around. And we have described some results for black holes from this approximate method. Remember, all these results are derived by this approximate quantization method for gravity. But there are some questions about black holes which we cannot answer using this approximate method. So for example, what precisely comes out of a black hole? So if you throw in some matter into a black hole, you can throw water, or you can throw I don't know, gold, and what comes out seems to be just radiation. Can we recover the information of the matter that formed the black hole? And in other words, is this process of black hole formation and evaporation consistent with the laws of quantum mechanics, which says that this information cannot be destroyed? Now, to answer this type of questions, we need the full theory. So now we'll return to the discussion of the full theory. And we really don't have a full theory, but we have a theory under construction, which we call string theory. And now we are having this conference on string theory. And the goal of this conference is to make progress in the construction of this theory, understanding this theory better and extending its range of validity of the things that we understand now to understand more things about this theory. Maybe one way to say this is that our picture of the theory is something like this picture. Okay? So you can see there is a building there, and you're pretty sure there is a building, but we don't have the sharp outlines. We don't know everything about the theory. We have some idea about the theory. Now, my attempt today will be to try to give you an idea without formulas, without mathematics. It will be more impressionistic. Hopefully, you will get the idea that there is some picture, but that will remain to be seen. So what we're going to try to see now is that, well, I'm not going to describe this theory in detail. I'm going to discuss one aspect, which is that we're learning some interesting things about the quantum aspects of black holes. And so we'll focus on one particular aspect. And the aspect that we will focus on is the idea of space-time as an emergent concept. Now, we can motivate this as the following, let's say, question. These are the type of questions you have in the university entrance exams in the US. I don't know if you have those in Canada. But so these are questions about analogies. So water is to atoms as space-time is to. So what, you know. So we use atoms to describe water. What are the things we use to describe space-time? So space-time atoms, you would say. Are there something like this? And the idea is similar. So we'll talk about an idea that is somewhat similar. But these elementary atoms, or sometimes we call them qubits. So qubits is the basic amount of quantum information, or the basic degree of freedom in quantum mechanics. These atoms are not local in our space, but they are really sitting far away. Okay? And so this is the idea of holography. And the idea is that, so we understand this in some special cases. So some universes with a constant negative curvature. And in these universes, they have, in some sense, some boundary, some region very far away. And in these universes, we can describe everything that is happening in the interior in terms of some qubits, some quantum degrees of freedom that live on the boundary. And these degrees of freedom are interacting a lot with each other, but they don't have any gravity. So gravity only exists in the interior. This is a kind of little picture for this. So the idea is that we have two separate descriptions, two different descriptions. One is we could have a particle moving in the interior. So in these spacetimes, there is a kind of gravitational potential well that keeps particles moving in the interior. Then you have other particles that this funny motion that is represented here tries to give you the idea that these particles are strongly interacting with each other. Now you can ask, well, how you would describe a black hole in this way? So in these spacetimes, you could imagine that you have a black hole in the interior. And the idea is the black hole would correspond to a large number of particles that are strongly interacting and live at the boundary. Okay? And the temperature and entropy of the black hole would come from the temperature and entropy of these particles that live at the boundary. So the idea of this description is that the theory on the boundary obeys the rules of quantum mechanics, and so therefore, so does the black hole in the interior. And then the black holes are consistent with quantum mechanics. But for that, you need to accept this holographic conjecture that space-time and the boundary theory are related in this way. So we'll come to the discussion of emergent geometry. So in this description, geometry is emergent in the following sense. So we have some space-time, and the qubits live far away at the boundary. But the gravitational space-time has one more dimension. So let me try to explain how that happens using an analogy. So imagine a sentence. So we come back to this idea of a sentence. And the sentence says, if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. Now, when you heard this sentence, you probably in your mind divided it into various words, and then you probably grouped the words in some way, analyzing the grammar of the sentence and so on, and the meaning of the sentence. You found the various sub-sentences or sub-clauses and so on, and until you got the full sentence. So in fact, there were also long-distance correlations, for example, between the word man, his, and he, or between the concept of keeping pace and drummer. Okay, that's a kind of deeper level correlation. As we include more words in our analysis, we get to a deeper meaning of the sentence. Okay? So we have, in some sense, an extra dimension, which is the depth of meaning, or the direction of meaning in the sentence, of how deeply encoded is a particular concept within this sentence. So in this analogy, the idea is that the state of the quantum system is analogous to a very long sentence that lives at the boundary. And the bulk geometry is doing some analysis of the meaning of this particular sentence.